Good morning. I'm Dr. Javed Ali, Professor, Department of Information Technology, St. Joseph Institute of Technology. Today we'll see a major concept or important concept of error detection and error correction. In computer networks, if you see error detection and error correction actually takes place in two layers. One at the data link layer, and the same is repeated at the transport layer. So what is the difference between these two types of activities is actually the activity is one and the same. What procedure, what protocol you follow at the data link layer, the same procedure, the same protocol is followed at the transport layer. Only difference is the scope. In data link layer, the uh, entities that are considered for this error detection and error correction is the adjacent nodes, next to next nodes. Okay. Whereas if you see the entities that are involved in error detection in transport layer is end to end, sender and the receiver. So we'll not be considering the intermediate nodes. We'll be considering only the end to end nodes, sender and receiver. Okay. So, but basically the process is same in both the layers. Okay, so we see the process. So basically, we have many error detection and correction protocols. So we focus upon one particular protocol, vastly applied protocol. It is CRC, cyclic redundancy check. Okay, so how error is detected using cyclic redundancy check is explained using an algorithm. Okay, so if you see, the algorithm is explained with the help of diagram. So on the right side, we have the sender. So what we are going to do is we are going to consider a data which will be either given as a polynomial, or it could be a sequence of bits. Okay, and what we have to do as a first step is we have to append n number of zeros. N number of zeros append to the data. Okay, so how many zeros to be appended? It will depend upon the divisor. Okay, it will depend upon the divisor, which could be also be a polynomial, or which could be a sequence of bits. Okay, so if you see, the zeros that are appended are n bits, and the divisor will be n plus 1 bits. Okay, for example, if divisor accounts for 5 bits, the number of zeros that are appended will be 4. Understand? The number of zeros in number of bits in the divisor, if it is counted and it makes up to 5, then the number of bits that will be appended in the data will be 4. Okay, so that is the difference between n plus 1 bits and n bits. So the bits in the zeros will be 1 lesser than the number of bits that are present in the divisor. Okay, now you will be presented with a data section and a divisor part. Okay, and we have appended the number of zeros, and we carry out the binary division, and the type of subtraction that is followed is modulo 2 subtraction. Okay, so modulo 2 subtraction. So what happens here is, usually while performing subtraction, we'll be going for 0 minus 0. Okay, 0 minus 0 is actually 0, and 1 minus 1 is actually 0, and 1 minus 0 is 1. 1 minus 1, 0 minus 1 is considered as 1. That is the only operational difference in modulo 2 subtraction. I'll repeat once again. So when we perform binary division, we carry out modulo 2 subtraction in CRC. So what is modulo 2 subtraction is, normal subtraction, 0 minus 0 will be producing a 0, 1 minus 1 will be producing a 0, 1 minus 0 will be producing a 1, 0 minus 1 will produce a 1 in modulo 2 subtraction. Okay, so after performing this type of division and subtraction, modulo 2 subtraction, we'll be getting a remainder. So that reminder, we regard it as CRC, cyclic redundancy check. We regard it as cyclic redundancy check, which is nothing but the reminder that is obtained after dividing the given data with the given divisor. Of course, following the first step by appending zeros. Okay. So now, once you get the CRC divisor, okay, CRC reminder, we have to transmit the data from the sender side to the receiver side. So before transferring, what we will do is we'll remove the zeros what we have appended in the first step, and we'll replace it with the remainder what is obtained. Okay, so we have obtained some remainder, right, after dividing, and that remainder will replace the zeros what we have appended in the first step. So we are transmitting the data along with the CRC. Okay, so CRC is nothing but the remainder what we've obtained as shown in the screen. So now this section, this block will be received by the receiver. At the receiving side, again we'll perform the binary division for where we perform modulo 2 subtraction. Okay, so while performing this, and at the we have to note down the remainder. If the remainder what we obtain is zero, if the remainder what we obtain is zero, then the data is free from errors and it can be taken up for processing. On the contrary, if we get a remainder other than zero, then the data contains an error and we have to go for error correction process. So now what we have performed is error detection. We have detected an error. So error detection is nothing but on the receiver side, after performing the division, if we get a value other than 0 as remainder, it indicates the presence of an error. If suppose the division ends up with 0 remainder, then the data doesn't contain any error, it can be taken up for processing, right? Now we'll see this with an example. Example is worked out here. So here we have given two informations. One will be the data and one will be the divisor. If you count the number of bits in the divisor, it accounts to 4. Okay, so which means that, which is nothing but n plus 1 bits according to the algorithm. Now what we have to do is we have to append n number of bits to the n number of zeros to the data, so which comes for three zeros. So those three zeros are shown in shaded part. Okay, so this we'll do it prerequisitely, and then we'll enter into the division. So while dividing, we perform normal binary division, but the subtraction will be modulo 2 subtraction. So if we see in the first step, so it goes for one time, we'll write it as 1101, and while performing the subtraction, 1 minus 1 is 0 and 0 minus 0 is 0. If you see 0 minus 1 is 1. So that is the only difference between normal subtraction and modulo 2 subtraction. If it is a modulo 2 subtraction, for 0 minus 1, we write it as 1. If it is a binary subtraction, we'll go for borrowing. But here, no borrowing is allowed. Since it is a modulo 2 subtraction, 0 minus 1 will yield a 0. Sorry, 0 minus 1 will yield a 1. So that's what we get. We proceed in the same format. So after completing, we bring the zeros down from the divisor part, and finally we come to the remainder part. We get the remainder as 001. We get the remainder as 001. Remember, what we have performed is a simple binary division, and the type of subtraction what we have performed is modulo 2 subtraction. The only difference in the modulo 2 subtraction is when we perform 0 minus 1, the result will be a 1 instead of borrowing. Okay, so here we'll write it as 0 minus 1 equal to 1. So after performing all these steps, we get the remainder. Now the sender has to pack this remainder along with the data. That is, it has to remove the appended zeros with the received remainder, and it has to transmit the data to the receiver. So now on the receiver side, we carry out the same division. If you see, the last three digits are replaced by the remainder. If you see, the remainder what we have obtained here is 001, and we are replacing the triple zero what we have added in the first step with 001, and we are carrying out the binary division with the same data appended with the remainder and with the same divisor, right? So when we carry out this binary division, of course with modulo 2 subtraction, where 0 minus 1 will yield a 1, we get no remainder. We'll get a no remainder. Okay, so no remainder is obtained as it can be seen on the screen. So the according to the algorithm, on the receiver side, if the division yields a 0 as a remainder, it means that the data doesn't contain an error. The data can be considered for processing. If suppose the division yields a remainder other than 0, then it has to be considered as a error prone data, and the data has to be put up for correction purpose. If upon successfully correcting the error, we can use it for processing. In case error correction cannot be carried out, that is, the destruction of data is too much, then there is no other way other than asking for retransmission of data. So before asking for retransmission, the protocol will try to correct the error by itself. So when it can't correct the error, then it will ask for retransmission. Okay, so this is the concept of error detection. So in error detection, there are many number of protocols that are used, and we have discussed a single protocol which is cyclic redundancy check. So where it is a step-by-step process. The first step will count the number of bits in the divisor, and will add one bit lesser than the number of bits found in the divisor uh, to the data. That is, will append n number of bits to the data, and the divisor will contain n plus 1 bits. Okay, so that concept will be slightly confusing. So remember, we have to add we have to append n number of zeros, whereas the divisor will have n plus 1 number of bits. Okay, so one bit lesser than in the account of zeros should be appended to the data. Okay, and we carry out the normal binary division, and will perform modulo 2 subtraction. So the difference in modulo 2 subtraction is 0 minus 1 will yield a 1. Okay, so after performing the division and subtraction on the sender side, we'll get a remainder. That remainder has to be replaced by the zeros what we have appended in the step 1, should be replaced by the remainder what we have obtained in the last step. Now the data along with the remainder will be transmitted to the receiver. On the receiver side, with the received data along with the remainder with the same divisor, will perform the same operation. We'll perform the modulo 2 subtraction and with binary division. Okay. So at the end, we'll be receiving a remainder. If the result is a zero, it concludes that the data that has been received is free from errors and can be taken up for processing. On the contrary, if the division what we have performed yields a remainder other than zero, then it means that data contains an error. Okay, and it has to be discarded. So what we'll do is we'll try to correct the error by the error. The protocol will try to correct the error by itself. Upon successful correction, the data can be taken up for processing. On the contrary, if the data cannot be corrected by the protocol, okay, that is the extent of damage is too much, then it cannot correct the error by itself. Okay, so in such case, it will ask for retransmission. Right, now we'll go for. So this is how a polynomial data can be converted into a bit format. So there are equal chances of the data being in the format of bits or in the format of polynomial. So if it is in the format of polynomial, by looking at the powers or exponents that are present, we replace it with 1, and those exponents that are not present will be declared as zeros, as shown in this example. Okay. Now coming to the error correction. So error correction, we'll see how a single bit error is corrected. We'll see with an example how single bit error is corrected. Okay. So for error correction, we'll be following the Hamming code. So Hamming is the name of the scientist who have discovered this particular code. Okay. So coming to Hamming code, we have first step. We need to find will be all the data, the information what will be provided with this just the data. Okay, we'll have only the message. Okay, so we consider it as m. The number of bits in the message is considered as m, regarded as m. Okay, now we want to find out how many redundant bits are required. Okay, so we need to know what is why we go for redundant bits. So these redundant bits will assist in finding out, or of course they are dummy bits. Okay, they are mainly used for the purpose of error correction. So once the mission is satisfied, once the error is corrected, these dummy bits can be dropped. They need not be considered for processing. Okay, so their main purpose is only for assisting in detecting and correcting the error. Okay, once the error is detected and corrected, they say they have served their purpose, they can be removed from the data sequence. Okay, so we need to find how many redundant bits will be required. Okay, so to find the redundant bits, we need to adopt the formula which is done with the help of trial and error method. The formula is shown on the screen. So it should be 2 power r greater than or equal to m plus r plus 1. The condition is 2 power r. R represents the number of redundant bits, which should be greater than or equal to m plus r plus 1, where m represents the number of bits that are present in the data. Okay. So, for example, assume message has the 7 bits. So we try substituting r equal to 0, r equal to 1, r equal to 2, r equal to 3, etc., etc., till a particular value of r that satisfies the given condition. Okay, so once the given condition is satisfied with any particular value of r, then that number, that R value is considered as the number of redundant bits. Understand? So we have to try uh, carry out the trial and error concept by substituting different values for R, okay, variable R. So whichever value of R that satisfies the condition, that value of R is considered as the number of redundant bits. Okay. So once the R value is found, for example, we are finding R as 4. We are finding, consider, imagine we have found R equal to 4. So once, meaning is, if you substitute in the formula or the given condition 2 power R greater than or equal to m plus R plus 1, the value of R equal to 4, the condition is satisfied. So we assume that there are 4 redundant bits. Now we need to find out which positions these redundant bits occupy among the data bits. Okay. So the rule according to Hamming is they will occupy the powers of 0 including 2 power 0. So they'll be occupying the positions of powers of 0 including 2 power 0, which means they'll be placed at, at the positions of 2 power 0, 2 power 1, 2 power 2, 2 cube. Totally we have 4. Okay, so up to 2 cube we need to consider. Okay, so 2 power 0 means position 1. 2 power 1 is position 2. 2 power 2 is position 4. 2 power 3 is position 8. So redundant bits will be present at 1, 2, 4, and 8. Right now, we don't know the values of these redundant bits R1, R2, R3, and R4. So simply we write it as R1, R2, R3, R4, and we need to find out. The next step will be finding what these values of R1, R2, R3, and R4 will be. Okay. So to start with, we begin with R1. Okay. So we begin with R1. So R1 among the data that is on the screen from 1 to 11, we have data bits and the redundant bits. Okay, so we are going to find the value of R1. So in which position we have to, and one more thing is, we need to decide which parity we are going to follow, odd parity or even parity. Odd parity or even parity. Okay, so odd parity means the number of ones should be in odd numbers. Even parity means the number of ones should be in even numbers. Okay, so for in this example shown on the screen, we follow the odd parity. So we need to write down the positions which we have to consider for the cross verification of number of ones. Okay, for each R1, R2, R3, and R4 as shown in the screen. Okay, so how these numbers are obtained? How these numbers are obtained, we need to know. For example, R1. So we need to check the positions of 1, 3, 5, 7, 9, 11. So how these positions 1, 3, 5, 7, 9, 11 are obtained? So we have to write down the bits in BCD format, in 4-bit binary, starting from 1 to 15, starting from 1 to 15, where 4-bit format of 1 is 001, 4-bit format of 2 is 0011, sorry, 0010, and 4-bit format of 3 is 0011, 4-bit format of 4 is 000100. So like this we have to write down the values of decimals in binary in 4-bit format. So once we have written this, rightmost column indicates R1, the next one indicates R2, the next one indicates R3, and the leftmost will indicate R4. Okay, now we have to look into the column 1. Now we have to look into the column 1, that is the rightmost column. We have to pick out those numbers which yield value 1 to the particular number. For example, 1. So value of 1 is 0001. So the fourth position is 1. So we have taken it as 1 for checking. And next thing is 3. So value of 3 in 4-bit decimal is 4-bit binary is 0011. So the fourth position is 1. Similarly 5. So 5 is 0101. So fourth position is 1. So likewise we have to choose all the numbers or pick all the numbers that yield a value of 1 to the rightmost bit. And similarly for R2, we have to choose the second column from the right, okay, which yields 1 for all the numbers. And similarly for the value of R3, we need to choose those numbers that yield a value of 1 in the third column from the right. Okay, and finally for the R4 bit, R4 positions, we have to look out for the leftmost column which yields a value of 1 for the numbers, and we have picked out those numbers, and those numbers are shown on the screen, right? So for R1 it is 1, 3, 5, 7, 9, 11. R2 it is 2, 3, 6, 7, 10, 11. R3 it is 4, 5, 6, 7, and R4 is 8, 9, 10, 11. So these are the positions where we are going to cross verify. These are the positions where we are going to cross verify. Okay. So now it is written here likewise. Okay, so now we are going to check for R1. We are going to check for R1. So we need to look into positions 1 3 5 7 9 11. Okay, 1 3 5 7 9 11. According to this screen, 1 3 5 7 9 11. So leave out the position 1 and pick out the bits that are present in 3 5 7 9 11. 3 5 7 9 11. So if you look at the position 3 5 7 9 11 on the screen, 3 is 1, 5 is 0, 7 is 1, 9 is 0, and 11 is 1. Okay, so if you count the number of ones, if you count the number of ones, it is 1, 1, 2, 3. So it is already odd. It is already odd. So we have to consider it as 0. We have to consider it as 0. So in the example, it is considered as even. Okay. So since there are 3 even ones, so odd number of ones has to be make up. So we are we are fixing the value of R1 as 1. I'll repeat once again. The current example follows even parity. So we are going to pick up the values of bits in the positions 3 5 7 9 11. So if you pick up the values of bits in this position, we are getting triple one. So triple one is a odd numbered one. So to make it an even numbered one, we have to add one. So that is done for R1. Similarly for R2, so we have to look out in these positions 2 3 6 7 10 11. 2 we have to leave. So we have to extract the bits from 3 6 7 10 11. So we have to count the number of ones, and if the number of ones is odd, we have to add a 1. If the number of ones is already even, then we have to add a 0. Okay, so 1 should be added only when the number of ones are odd. Count of number of ones is odd. 0 should be added when the count of number of ones is even. Okay, so accordingly we find the values of R1, R2, R3, R4. Okay, and now we'll deploy these values among the data in the corresponding positions of R1, R2, R3, R4. Okay, and then we'll transmit the data. So receiving, what we have to do is upon receiving, what we have to do is, so we have to extract the values of R1, R2, R3, R4 from the received data sequence, and we have to find what value it yields. So the value that should be yielded by these bits R1, R2, R3, R4. Again, we have to perform the same procedure. For R1, we have to check 1 3 5 7 9 11. Similarly, for R2, we have to check 2 3 6 7 10 11. For R3, we have to check 4 5 6 7. For R4, 8 9 10 11. So in these positions, we have to extract the number of bits and we have to count the number of bits. If they are odd, we have to make it as 1. The corresponding bit should have a value of 1. If they are even, the corresponding bit should have a value of 0. So likewise, we have to pick out the bits for R1, R2, R3, R4, and we have to write it down. So if the value is 0, then the data doesn't contain any error. It can be taken up for processing. Okay, it can be taken up for processing. On the contrary, if the data contains any error, if the data contains any error, that is, it yields a value other than R1, R2, R3, R4 put together, they are yielding a value other than 0. Okay, the decimal value other than 0 is obtained. So now what we have to do is, the decimal value indicates the position of the bit in the data sequence that is reversed, that is error prone. So for example, if you are obtaining 0 1 1 1, for example 0 1 1 1, which is equal, the value of R1, R2, R3, R4 is 0 1 1 1, which means it is equal to decimal value of 7. So which should be interpreted as, the bit at position number 7 should be reversed. So if it is 0, convert it as 1. If it is a 1, it convert it as 0. So that's how we perform a error correction. That's how we perform an error correction. So whatever values on the receiver side, the R1, R2, R3, R4 for even parity yield, so that should be converted into a decimal number. So if they are already 0, then there is no error at all. If the R1, R2, R3, R4 are yielding a value other than 0, it has to be converted into a decimal form, and the decimal position, it is nothing but the position of the bit in the sequence that is error prone. So that position should be reversed. The value of the bit in that position should be reversed. If it is a 1, can make it as a 0. If it is a 0, make it as a 1. Then we are done. So we have found out a single bit error and we have corrected a single bit error. Thank you.